Welcome to this tutorial on face recognition with the video streaming from the cloud. In this face recognition tutorial, we are going to explore different steps involved in achieving real-time face recognition. And for the cloud streaming, we are using Chrysalis Cloud. We have developed Chrysalis Cloud to be the easiest and fastest way to collect and analyze video. There are two parts. Let's begin by setting up the webcam from our laptop to stream to the Chrysalis Cloud. To begin, let's visit the Chrysalis Cloud website. You can see the URL here. It's chrysaliscloud.com. You can go through the website and see how we have developed this new technology to stream to the cloud, which can be used by anyone, a developer or a enterprise, for cheap and efficient and reliable streaming. So for developers, let's begin by visiting the console. You need to create your account. It's free for 1 month. You can sign up here. I've already signed up and set up my account, so I'm just going to log in. And once you log in, you have various resources here. There are some AI examples which we have developed, some developer resources which guides you through using Chrysalis Edge proxy, which is our edge solution, and also our cloud solution, which is the Python SDK. But now let's focus on streaming our webcam to the server, Chrysalis Cloud server. So if you go and click on this RTMP server, creating our first RTMP server, you'll get the screen and you can name the camera whatever you want. I'm just going to name it as tutorial 101 and start. It just takes a few seconds and you should be up and running by now. That's it. So you have a streaming server with the credentials. There is a RTMP server URL. There is a server stream key, and this is the stream URL with the stream key embedded, so that it's easy for you to copy and stream. And this is the SDK, which will be coming and using later. So let's focus on these details here. All we need is the RTMP stream URL here. Copy this. Once you have copied the RTMP stream URL, you should be ready to stream your webcam to the Chrysalis Cloud. Let's go and look at the developer resources. It has some instructions on how to do that. So if you click on developer resources, there are different methods listed here. Right now I'm going to be using my Mac Facetime camera to stream to the cloud. So click on this, and then there is a blog which basically tells you how to stream the Mac camera to the Chrysalis Cloud. Basically you need FFmpeg. It's pretty straightforward. Just install FFmpeg. I have already done that, and once you do that, you just need this command. The RTMP stream shown here is an example. You will need the RTMP stream, the URL that is here in your console. So let's go to our terminal and start streaming the webcam video to Chrysalis Cloud. I hope the FFmpeg install was smooth. I have the streaming command handy here, FFmpeg. it basically helps you stream your webcam to any RTMP server. So this is the command. You can copy the ffmpeg stream command from the tutorial and the RTMP URL from your console. Concatenate these two and then you run that in the terminal. Your webcam should start and it should be streaming to your console now. You can verify that it's streaming and you have the video by checking the video in the console. This is the console here. Just refresh so that it gets updated. The video now and see the live video that is being streamed to the console. The video might be a bit delayed, but it'll show up. I'm going to pause the video for now. So let's go to the Python SDK and see how to access the live video stream. These are the credentials that you'll be needing, but the instructions to use the Python SDK can be found under the developer platform resources. So check the resources, SDK basics, and the Python Cloud SDK because we'll be accessing the cloud video stream. Once you go to the blog that is linked here, I'm going to link the blog in the video description. You can see the Chrysalis Python SDK. It has some explanation on how OpenCV video capture works and how it is not a good idea to use it even for RTMP streaming. There are issues like skipping frames and the frames being blurred. That's where we come in. We provide a solution which is super reliable and you don't have to worry about maintaining the stream or figuring out how to access the latest frame and stuff like that. So you can read the blog for detailed explanation of how the Chrysalis Python SDK works. Right now, let's go jump into it and check how it works. You need the Chrysalis Python SDK installed. We have created an YAML file, which is super easy to use, and that helps you install the Python SDK. You can copy this and in your folder, in your working folder, just go and create a new file and paste it there. I already have created an environment file here. So I'm just going to open up the location and edit and show you how the file looks. I have renamed the Conda environment as Chris face recognition because that's what we'll be doing, face recognition using Chrysalis Cloud. You save this file. Once the environment YAML file is edited, you can create the Conda environment by using the Conda environment create command. That's the command, and once you run the command, it should start creating the Conda environment for you. It takes a while. Once the Conda environment is done creating, you should see these messages at the end. This is the activate message, or the message to tell you how to activate the Conda environment. So let's go ahead and activate our Chrysalis Cloud face recognition environment, and you should see the Chris face recognition here. Let's clear this up so that it brings to the top of the screen. You can see the environment name here. We can now access the live video stream from the cloud. You can read about it in the Chrysalis Cloud Python SDK blog, which has all the detailed instructions on how to probe the live stream and how to get the latest image from the live stream. I'll just jump into the Python example right away so that it's easy to follow. I've already created a Chrysalis video display Python file, import the necessary packages, uh, import Chrysalis package, which is the Python SDK, and to probe the live stream or to retrieve the latest video image, you need some credentials to receive a secure live video link. Those are the port, host, password, and the certificate path. And you can find all these under the developer console. You go back to your My Cameras, and then in your camera, the SDK section. So the port is SDK port is 6115. Let's copy this and then have it in the port section. Assign it to the port. You need the host, which is this SDK endpoint. You copy this and then paste it here. And the next one is the SDK password. You can copy the password here using the copy key. And then have the password here. And the next one is the certificate path. And you can download this certificate using the download server key. It prompts you to download, and you can download in the location which we have here and save the location, save the path, save the file, and copy the file name. Since the Python file is in the same location as the certificate, you can just have the certificate name here directly and save it. We also need the extension, that is the .cer. So let's just create it at the end .cer. We now have all the credentials in place, and we can access the stream using chrysalis.connect command. The chrysalis.connect command along with the credentials will give you the live stream. This connect command is very similar to the video capture command from the OpenCV. And to grab the latest frame, you need the video latest image command, which is similar to the video read command in OpenCV. You put all this in a while loop so that you're continuously grabbing the frames, validate if the frame is present, and convert the frame to a Python readable format using .data command, and display the video stream using IamShow command from the OpenCV. This is the Python script, a very simple Python script to read and display the video stream that is being streamed to the Chrysalis Cloud. Let's go and run this Python script and see if we are able to see the live video stream. You can see the live video stream here. So now we have the video streaming into the server, and we can access the stream pretty efficiently and quickly and without any delay. You can see that in the video. Now let's move on to the main step, that is the face recognition step. Let me close this stream for now. Uh, you can simply stop the stream here by Control C, and then it stops the signal that's being sent to the server. And we can close the video display Python script as well. Uh, so the main problem, that is the face recognition problem. To begin with face recognition, uh, there are many other solutions, as in well explored solutions out there, but we are going to explore some very simple and quick techniques that can be done through Python, and we will be able to recognize faces, new faces in the video stream that is being sent to the server. So to recognize a face, the machine has to know who the face belongs to. Uh, so the first step is to create a data set with faces and label them. Basically, a set of images in a folder along with the names of who the images belong to. For example, I have taken few set of images from uh, Google, basically Google search, uh, of characters from Jurassic Park and Brooklyn Nine-Nine. You can see some images here. Example image 1, 2. You can see that in each of these images, it's only one person whose face is visible, and the character name is the name of the folder here. Um, you can see that here. Another example is from Jurassic Park. This is an image, and we have such similar images of different sizes, different colors, and different orientations as well. More the examples, the better the recognition is. So you can see this. I'm just going to close this now. And the character's name is again the folder name. We will come back to this image dataset later. So the first step in face recognition is obtaining some sort of features that can be used to describe the faces, and this step is called feature extraction. Today we are going to talk about a couple of them. The first one is histogram of oriented gradients, shortly known as Hog Features. We'll jump right into how Hog Features are calculated. So to calculate a Hog descriptor, we first need to calculate the horizontal and vertical gradients. These are done by filtering the image with kernels, and those kernels are represented as such here. The horizontal kernel gives you the horizontal gradients, and the vertical kernels give you the vertical gradients. Basically, filter the images with these two kernels, and we should have the horizontal and the vertical gradients. The next step in this is to find the magnitude and direction of gradients at each pixel location. The magnitude is basically the square root of sum of the squares of vertical and horizontal gradients, and the direction is tan inverse of these two gradients. Uh, the x gradient fires all the vertical lines in the images, and the y gradient fires all the horizontal lines. The magnitude of the gradient fires whenever there is a sharp change in intensity, and when there is no change in intensity, none of the gradients are fired. Um, you can see that in the example that I'm going to show later. The next step in the calculation of Hog features is to divide the image into 8 cross 8 cells. Here is an example where the image is divided into 8 by 8 small cells. As you can see here, this is the entire image, and this is one 8 by 8 cell. And here you can see the gradients that are being fired. Some of the horizontal gradients are prominent horizontal gradients are these, uh, and the vertical gradients are these. This is where the changes occur from dark to light and light to dark. These are the intensity changes that should be noted and not the color changes. And after dividing this cell into 8 bar, I mean, dividing the image into 8 bar 8 cells, uh, we need to represent it in a format of histograms. The histogram is created by dividing the gradient magnitude values and directions into bins. Uh, so there are 9 pins that are created from 0 to 160 degrees, and each bin is 20 degrees. So in the we can the see this one, for example. This 8 by 8 cell block contains the gradient direction, and this 8 by 8 cell block contains the gradient magnitude uh, from this region. This is an example. Uh, Now let's see how to convert this into histogram values. When you look at these 8 by 8 pixel values, a bin is selected based on the direction, and the vote, that is the value that goes into the bin, is selected based on the magnitude. Let's focus on the pixel that is circled blue here. It has an angle of 80 degrees and the value of 2. So it adds 2 to the fifth bin, which is 80 degree. And if you look at these values, the values that are circled in red, the gradient values 10 and 4, uh, it's a bit different. The 4 corresponding angle is 10. It's halfway between 0 and 20. So the vote of the pixel splits evenly into two bins, as 2 and 2 between 0 and 20. The magnitude value is split into 2 because it's exactly half. We do the similarly for all the values in 8 by 8 cell, and we create a 9-pin histogram. And for the patch that we have analyzed here, the histogram should look something like this. We then normalize the histogram for this entire block so that the feature descriptors are immune to lighting changes and other such factors. By normalization, we mean composing the value between 0 and 1, the mathematical operation of normalization. After this step yields a 36 bar 1 feature vector, and this process is repeated for the entire image. For say for this entire image, and the histogram is calculated again, and this gives you the Hog feature vector, which is histogram of gradient feature vectors. All this explanation seems complicated, but all this can be achieved by one single command from Python. So I already have written a Python script for extracting the Hog features. Let's go and explore that. This is the main function, and before looking at the main function, let's look at the imports, the necessary packages. Schemage is a necessary package, and the Chrysalis is a necessary package. The schemage contains the Hog function, which gives you the histogram of oriented gradient features, and the Chrysalis package is used to connect to the cloud stream and extract the frames. If you look at the main function, we have all the credentials here, and then the chrysalis.connect, which connects you to the cloud stream and video latest image. gives you the latest frame that is in the server. The create hog image is the function that is used to create the hog features. Let's go and check out this function. This contains some explanation about the algorithms, and this is the command that is used to get the hog features. Uh, so hog, yeah, is the function that is part of the ski image package, the single command that I was talking about to get the hog features. You pass the image as input, and these are some of the optional uh, values or parameters. I have chosen these parameters to be optimum, as in provides an optimum histogram of oriented gradient values. Orientations is nothing but the number of orientation bins, and pixels per cell is the number of pixels in each cell, and number of cells per block. Visualization is basically to see the hog features, and multi-channel is for color images. So you're both giving it as true. And then you rescale the intensity for better display, and then the hog images return, and hog images return to the function, and the hog image is being displayed. We'll go and run this Python script and see how the hog features look. So I had stopped the stream to the cloud, so let me restart that. It's streaming now, and let's run the Python video hog script. Looks like this key image is not installed, so maybe we can edit the environment file and then reinstall that, or we can just install here using pip install ski image. Looks like it's the ScienceKit image package and not the ski image. I'm sorry about that. Let's try again. Yeah, this works. Now the ScienceKit image package is installed. Let's run the video underscore hog.py script, uh, the Python script, which gives you the hog features. The live video that is being streamed to the Chrysalis Cloud is accessed, and the hog descriptors is run on that video. Uh, let's check the output. Here you can see the hog descriptors. The video that is being streamed to the cloud is my video. You can see the hog descriptors are predominantly along the shoulders and the edges of the face. Uh, the higher intensity ones are the gradients with high magnitude, and the orientation of the arrow marks here represent the direction of the gradients. As you can see, it kind of represents the face and the sharp edges. And once I move my hand, you can see the gradients moving along the image. The descriptors kind of represent the face. These are the descriptors that we'll be using for face recognition as features. How features are easily describable and can be stored easily, hence we use hog features. Now the second part, let's go and check that out. The second set of features that we're going to talk about is facial landmarks. Facial landmark detection involves localization and representation of salient features on their face, such as eyes, ears, eyebrows, nose, mouth, and jawline. Detecting these facial landmarks is a two-step process. The first one is localizing the face in the image, and the second step is extracting these key facial structures on the face ROI, that is the region of interest. There are numerous ways to locate faces, but we are going to use DLIP face detection to locate the face in the image. It is super simple and can be done in a couple of steps. Once the face is localized, the next step is to detect the key facial landmarks. This is fairly complicated problem, but fortunately for us, the DLAB facial landmark detection library provides us provides us with a location of 68 coordinates. The that is the XY coordinates on the image that map to facial structures on the face. Uh, let's look at the code for the facial landmark detection. Uh, I have the code ready. Let's open it and go through the code. So again, we import the necessary packages, the DLAP package, which contains the face detection, facial landmark extraction packages, libraries, and our CV2 for displaying images, and Chrysalis Python package for video streaming extraction from the server. We begin similarly as before by providing the credentials and then connecting to the stream. Uh, and then for the DLIP facial detector, there are sh- shape predictor and landmarks data file which contains similar datasets or facial datasets which have been explored and stored in the format that the DLIP can analyze and use to identify a new face or predict the landmarks on the new face. So we'll use this shape predictor for this purpose, and the download link is in the description. The DLIB get frontal face detector that gives you the face detection. It's a single command. Basically, it looks for the face in the frame and provides a rectangular coordinates around the face. Uh, so let's go and explore that. We grab the latest frame using video latest image. We resize it for visual purposes so that it looks bigger for now, and convert that to grayscale for face detection. Uh, the detector does the actual detection process and then returns a rectangles which contains faces. If there are multiple faces, it returns coordinates of multiple rectangles. Each four coordinates representing the x, y, and the width and height of the rectangle of one face. So we loop over all the face detections and then determine the facial landmarks for the face using this predictor and display it by drawing a circle around the facial landmarks on those x and y coordinates where the landmarks have been returned, and display the facial landmarks. Let's go and run the Python script. The video is being streamed to the server. Let's run the Python script facial landmarks, and we should be able to see video where there are 68 points on and around the face across the mouth, on the eyebrows, on the eyes, and the nose, basically indicating the salient features. These salient features are unique to each person, and these are the features that will be used to detect the or recognize the face later in the face recognition step. Uh, you can see as I move around, the landmarks also move around on the image. That is basically the DLib is doing its function and recognizing the landmarks correctly. The next step is to create a facial encoding of these landmarks for the recognition system to learn which face is whose. The recognition system works best when the person is directly facing the camera, but that might not be the case for all the images that we have in our dataset. Fortunately, there's a technique known as face normalization, which can be used to align faces such that it looks like the person is directly looking at the camera lens. More such images, better the face recognition system. Again, DLib comes in handy here to do the face normalization part. Uh, let's look at the face normalization code. Uh, I have written a Python script here known as face alignment. The same steps as importing the necessary packages. Uh, and for facial alignment, we don't need 68 landmarks. That is overkill. We just use 5 landmarks. A data file which is a composition of 5 landmarks for so many different faces that we will use. We'll connect using the Chrysalis connect and do the same process as detecting the faces using detector. The detector from DLab detects the images and we find the landmarks that we need to do the alignment. Full object detection gives you those 5 landmarks and we append the number of faces that are being detected in the frame. If there are more than one face, you have multiple faces that are being shown. This is the display command, which displays the rectangular boxes around the face, and this part gives you the face aligned images. The get face chip command is the one which does the alignment of the face. Let's run this Python script and see how it looks. Let's stop the previous script and clear the terminal and run the facial alignment script. As you can see, there are 2 data files here. One is for 5 facial landmarks and the other one which contains data for 68 facial landmarks. Let's run the face alignment script and see how the face alignment works. This is me looking directly into the camera and this is the aligned face, as in it basically returns what the original images. But let's tilt the head and see how it works, how it looks on the aligned face. You can see that my head is tilted in the original frame, but it looks as if I'm directly looking into the camera in the aligned face. When I tilt in the other direction, the same thing happens. So this is called as face alignment. Once this is done, you have more images with faces directly looking at the camera, and you can use this, crop this image, as in crop this rectangular box and use it for face building the face data set. You can run this on all the images in the folder or um, capture more images from the live webcam or from videos, whatever your heart desires. So as you can see, the face alignment helps us in creating crops of the faces that looks like it's being directly seeing the camera, the faces are seeing the camera. So uh, let's use this to create the data set. To add images to the data set, I have written a script where you can use your webcam to capture your images. Let me just go through that script briefly. Uh, this is that script. The main arguments needed for the script are the dataset path, uh, as described here, dataset path which is required, and the name of the person who's sitting in front of the camera. It helps if there's a, it's best to have just one person in front of the camera so that there are no multiple faces being recorded into the same uh, data set at the same under the same name. The count is the number of pictures that you want to take. Video stream source captures the video from the webcam, and the rest of it is just simple uh, functions which reads the frame and then saves it as a picture in the desired folder. So let's run this script and create our face or my face in this dataset. Like I said, the parameters are essential. -d is the dataset path. That would be the images folder. Name is my name, and the count is the number of images that you would want to capture. More the number of images, the better it is. But as you can see, dlib is super efficient, and we can use just 5 to 10 images for the purpose of recognition. It should do pretty well with just this. Taking the pictures is almost done. Let's go and check the folder has been created, and there are 10 images named from 0 to 9. Let's see how it works with how the face recognition system works with this. So these are the images just for reference again, different angles and such. Now to move on to the actual face recognition part. For face recognition, we are going to be using an encoding system using CNN. The 68 facial landmarks that we had extracted earlier will be used to create the facial embeddings. We use these landmarks points to create 128 encoding values of each face, that is face represented by a 128 cross 1 dimensional vector. The generation of the 128 encoding values is done with a pre-trained convolution neural network, also known as CNN. The CNN used by the DLib is trained on millions of images of faces and is quite accurate in generating the embeddings. There are many articles on the web. If you want to do a deep dive on the CNN architecture, I have linked few of them in this blog. Here you can take a look at a simple architecture or the most common architecture of the CNN, where the input image has 168 facial landmarks. It goes through convolution pooling, and after passing through connected layers, you get a 128 values vector code, that is 128 cross 1 vector, which is basically the embeddings. Let's see how to create those embeddings. I have a Python script known as create facial encodings. This will, let's go through the process here. The script needs dataset input, as in which dataset it should use to create the encoding files. the file path for the encoding file, and the other optional inputs, detection method and remove existing encodings. The detection method is default hog, or we can use CNN. Uh, we can use CNN here if required. Uh, you can make CNN here so that it's easy, and you can keep hog as input and check it out and how it works. So you pass these arguments. The function create encodings looks for the images in the dataset path and checks if there are any known encodings for those images. Uh, if there are known encodings, it simply appends to the already existing encoding file. It goes through the images in a for loop uh, and then locates the face in each image and creates the facial encodings using the landmark detection, and then those encodings are stored as known encodings on, and along with the labels as known names. These are some of the timers just to see how long it will take to record the encodings. Now let's go and run this. Create facial encodings. The dataset path is images, and the hyphen e would be encodings, and a facial encodings pickle file. Make sure that it's a pickle file by naming it as .pkl, and rest of the parameters are optional. So I'm just going to run this, and it's going to take some time to create those facial encodings. Now the most exciting part, that is face recognition. So let's go through the code before we run the recognition script and seeing the output. We begin by importing some of the necessary packages, the face recognition package and the amutils package. Uh, these are some of the packages along with dlib, which helps you do the detection easily. We should import the Chrysalis package for accessing the live stream, and it should be these should be the necessary packages. Let's look at the necessary input arguments. The encoding file path, where we compare the current encodings with the encodings from our dataset. This is the detection method. Right now, it's the default is the hog description method, which is histogram of oriented gradients, the initial descriptors that we had mentioned, and distance tolerance. That is the amount or the value, the probability value, uh, which is used as a marking line. By default, it uses 0.5, but 0.55 seem to give a better recognition rate or recognition accuracy. Basically, if the machine says that with 55% accuracy or more that the detected face is belongs to the so and so percent, then that is the actual result. So hence the value 0.55 here. Uh, these are the credentials for accessing the stream, where we'll take the input frame from uh, the OpenCV has the frame in BGR format, so we convert it to RGB, resize it so that it looks bigger and better, and then we locate the faces using the face recognition module. the face locations gives you a rectangular tick boxes, and we also create facial encodings for all the faces faces that we have detected. Uh, and the recognition part is just this. In actuality, face recognition dot compare faces. Uh, the compare faces basically check the encodings of the newly seen, newly seen face in the webcam stream from the cloud and compares it to the encodings that is already present in the data set, and then calculates the Euclidean distance between the en- encodings. Euclidean distance is basically the sum of square root of the mathematical Euclidean distance. And if there is a match, that is the value, the Euclidean distance lies within the tolerance, then you have a match. Uh, if the match is true, we draw the boxes around the faces and say whose name it is. That's the part here and here. Loop over the recognized faces and draw the rectangular boxes and name them. The code is pretty simple. We should be able to run this and check how it works. So let's do that. Um, Before that, let's stream the video to the cloud. It's streaming to the cloud. Let's run the Python recognizer script, the face recognizer script. Provide the path to the embeddings file. This is the command, and you can see my face being recognized correctly in spite of changes to my face. Let's see if we can find other faces of celebrities that we have trained and recognize those. Let's start with Jurassic Park character. Sorry, it's taking long. Let's just see if we can recognize this image. Yeah, it does. Even though this image is an older version of Ian Malcolm, the system is able to recognize it correctly. I will now stream a video to the cloud which contains slides of some of the person's images that are in the dataset and some which are not, and see how that works. Let's check that. This is the output. You can see that the first image was recognized correctly. Here, even though both the person looks similar to the eye, the system recognizes correctly that one which is in the database and the one which wasn't. The person that's not in the database is marked as unknown. Here you can see that one person who's in the database is recognized correctly and the other person, Terry Crews in this case, is not detected. It says unknown. These are some of the other examples. And that's it, folks. You can see how simple it is to build a facial recognition system using Chrysalis Cloud and some simple OpenCV and DLib commands. You can build a more complex system by training new facial data from scratch and using complex classifiers like SVM, the scalar vector machines, or KNN, k nearest neighbors. Whatever techniques you choose to use and however complex the problem might be, the Chrysalis Cloud can support your live video stream for any AI applications. Visit chriscloud.com to find more fun tutorials and demos with our free developer trial. You can log in by going to the console here. Feel free to reach out to us anytime. You can reach out using the email hello@chriscloud.com. We would love your feedback. Thank you.